So, we've got this launching mechanism that's able to launch this projectile into the air using a spring. A great example of the conservation of energy in the projectile Earth spring system. We are going to set y equals 0 at this lowest point, the point when the spring is compressed. I'll draw that right here. That's a smart place to set y equals 0 because we're given information about the 25 meters being above that point, and it's the lowest point of the projectile's motion. All other gravitational potential energies will be positive if we set y equals 0 at that lowest point. Of course, you could set y equals 0 anywhere. You could set it at the place where the projectile is fired. You could set it 4 meters above that. It doesn't matter. So you can set y equals 0 anywhere. There is just an easier way to do this if we make it at the lowest point of motion. If we do that, solving for b, the spring constant of the spring, I can compare that lowest point, the compressed point, I can say that that's my initial position. So initial is the compressed point. And I'm going to say that my final position here is the highest point. Of course, the projectile will come back down and do things after that, but I'm going to only look at those two positions in my problem. And since I chose a system, the projectile, spring, and Earth, and there's no energy being added to that system, I can say that the initial energy equals the final energy in my system. So, in the beginning, I've got spring potential energy. And that's it. There's no gravitational potential energy. There is no kinetic energy at that point. It's released from rest. This is y equals 0. At the highest point, the ball travels up, definitely gains some height. So we have some gravitational potential energy at this final location. But no kinetic energy at that point. The ball isn't traveling up, isn't traveling down, and the spring is no longer compressed, so there's no spring potential energy. So I can go ahead and say that 1/2 spring constant multiplied by the amount that the spring is compressed initially squared equals the mass of the projectile times the gravitational field strength of Earth times the final height of the projectile. And solving for the spring constant, I know all of these values. They're given to me in the problem. And I was able to get a spring constant of 1,190 newtons per meter. Looks like some of these values have two sig figs, the 25 meters there. So I'll just say 1,200 newtons per meter. Always making sure that, of course, you convert grams to kilograms and make sure that everything else works. That works great. Now for part C, we're trying to find the speed of the projectile the moment that it leaves the spring. There are a lot of different options here. You could use your equations of one-dimensional motion and only focus on the projectile while it is in the air, realizing that that 25 meters is above the launch, the compressed point, not above the spring when the spring is relaxed. So you'd have to use 25 meters minus 0.120 meters there if you were going to use that as your delta y. We're in our energy unit, so I'm going to solve this problem using the conservation of energy. And I'll say that the initial energy is equal to the final energy. That's still true in my system. However, I'm going to choose a new final position. I'm going to set the final position now as not the highest point, but I'm going to choose the point when the projectile leaves the spring. If that's true, then I've still got spring potential energy in the beginning, And that's going to turn into gravitational potential energy at the end and kinetic energy. As the ball leaves the spring, it's got height and speed. So I need to pay attention to both those types of energy in my system. So 1/2 spring constant times the displacement of the spring squared equals the mass of the projectile times the gravitational field that the projectile is in times that final height, which isn't 25 meters anymore. It's just the 0.120 meters, plus the kinetic energy of the projectile at that point. And it's that final velocity squared that we are looking for. The speed of the projectile, we'd be able to get how fast that is moving. I worked through the math before, and I got a speed of 22 meters per second with all those values plugged in. Make sure that you can do the same, and looking at this problem, like just in summary, there are good applications of choosing an initial position and choosing a final position, and realize we can always compare those in an isolated system with energy. Looks good there. Make sure you can do this problem to this level.